The time evolution of a one-dimensional dynamic subsystem is described by the equation given here. If this has one stable and two unstable fixed points, then the parameter B satisfies which equation? So to solve this problem, we're going to take that, we're going to just use the law of conservation of energy. So what equation we are given in here is the equation for the velocity, right? Applying conservation of energy. So we're going to say the change in the potential is equal to the change in the kinetic energy. So half m dx by dt the whole square. So this evaluates to half m x plus the whole square d square minus x square whole square. So therefore now we can find an expression for delta Vx. So delta Vx, so we can evaluate an expression for delta Vx. Now what we need is the the stationary points. We first find the stationary points. We do the first derivative test to find the stationary points, and then we'll do the second derivative test to evaluate the unstable points. So when we do the first derivative test, we have to set this equal to 0, right? So we have to set this equal to 0. So this is the derivative is nothing but, so let's bring this 2 and m to the right side. So we'll take it to the right side, and when we evaluate the derivative, we get so this is what we get. Now this equation can be solved for x. Okay, so this equation can be solved for x. So we'll just simplify this equation and solve for x. So what we get is now from this equation itself you can tell that, you can see that this equation will go to 0 when x is equal to -1 or x is equal to plus or minus b. And when the second term b square minus x square minus 2x square plus 2x goes to 0. Now obviously for the second, we have to check the second derivative test in all these stationary points. So the second derivative for unstable equilibrium, the second derivative of the potential must be less than 0, or it should be negative, right? So it should be negative. So the second derivative of the potential, So you check the second derivative of these potential in these stationary points, and we get that 2p square minus 1. So this is what we get for the condition on B. So by this we can say that option C satisfies the equation.